The insane engineering of James Webb Telescope. If you want to see the current height of technology, you could do worse than taking a look at the James Webb Space Telescope. Millions have been doing just that over the past few months, given that this past Christmas Day witnessed the launch of the massive NASA project. As the successor to the now-venerable Hubble Space Telescope, the JWST is designed to go much further into outer space and thus see much further back in time, potentially to the formation of the first galaxies. Some 30 years in the making, and with an eventual price tag of $10 billion, the James Webb Space Telescope is simply not allowed to go wrong. Today we're going to talk about the insane engineering of the James Webb Telescope. I know what we're thinking. How is it possible to create a device that has the capacity to witness objects billions of light years away? Well, stick around to the end as we answer this intriguing question and more, as we delve deeper into the mechanics of the world's most powerful telescope and the pinnacle of human innovation. So let's begin the video. When the Hubble Space Telescope launched in 1999, it soon became obvious something was amiss. The images it sent to Earth were disappointing, blurry, and nowhere near to what scientists had expected. The problem was traced to the telescope's great mirror, which was improperly polished during manufacturing. A rescue mission involving a team of astronauts was sent to fix the problem. Hubble received glasses to correct its short-sightedness and turned into the astronomical powerhouse that has since generated thousands of iconic and scientifically priceless images. With the James Webb Space Telescope, rescue missions are impossible and therefore no failures are allowed. The James Webb Space Telescope, sometimes fondly referred to by astronomers as the first light machine, was built to see the first stars and galaxies that emerged from the dust and gas of the early universe, only a few millions of years after the Big Bang. Because these stars and galaxies are so far away, the visible light they emitted when the universe was only a few hundred million years old has shifted into the near-infrared and infrared parts of the electromagnetic spectrum. This strange effect, known as the redshift in astronomical jargon, is the result of the expansion of the universe and the ensuing Doppler effect. That's the same effect that distorts the frequency of a siren of a passing ambulance car. Infrared radiation is essentially heat and can be detected with special sensors that are different from those detecting visible light. Since the stars and galaxies that JWST was designed to study are so far away, the incoming signals are also extremely faint. The scientists and engineers behind JWST needed to tackle a range of technical obstacles to make this hoped-for detection possible. The James Webb Space Telescope will be far away from Earth indeed, about 1 million miles away. That's more than 4 times farther than the Moon. The telescope will orbit the Sun, while simultaneously making small circles around the so-called Lagrange point 2, a point on the Sun-Earth axis constantly hidden from the Sun by the planet. At L2, the gravitational pulls of the Sun and that of Earth keep the spacecraft aligned with 2 big bodies. But even that wouldn't make Webb cold enough to accomplish its mission. The largest piece of the spacecraft, and one without which the mission would be impossible, is its tennis court-sized deployable sun shield made of 5 layers of an aluminum-coated space blanket material called Captain. The sun shield will unfurl in space before the telescope reaches its destination in one of the most nerve-wracking parts of the spacecraft's post-launch deployment sequence. The sun shield is James Webb Space Telescope's main cooling mechanism. Nestled behind it, the mirrors and the 4 never-before-flown instruments will remain far below freezing at 390 degrees Fahrenheit. The sun-facing side, on the other hand, will be incredibly hot, up to 230 degrees Fahrenheit. The sun shield is not a simple parasol. A lot of clever engineering went into its design. The 5 layers of the ultralight Captain material are precisely spaced so that the heat absorbed by each layer is perfectly radiated away from the spacecraft through the gaps. While super thin and ultralight, the material is also incredibly sturdy, enough to survive bombardment by meteorites. To do what it has been designed to do, the James Webb Space Telescope really couldn't be small. The Hubble Space Telescope, with its mirror 7.8 feet in diameter, couldn't detect those distant early galaxies even if it were as cold as Webb. If you want to see those distant faint galaxies, then you need to gather more light. And so the simple fact that the Webb's mirror collects 6 to 7 times more photons in a given amount of time than Hubble gives it a significant advantage. The ability of a telescope to collect light increases within the square of its size of mirror. With its 21-foot mirror, Webb will not only be able to take sharper, deeper images of the universe than those made of Hubble famous, but will also be able to do so in a fraction of the time needed by Hubble. So are you guys enjoying the video? Here comes another challenge. How do you lift something the size of a tennis court with a 21-foot mirror into space? Can you guess? While you think, do subscribe to our channel and click on the bell icon to receive instant notification about all our future videos. The Hubble Space Telescope, which measures 44 feet long and at most 14 feet across, fitted quite snugly into the 60-foot long and 15-foot wide payload bay of the Space Shuttle Discovery, from which the telescope was deployed in 1990. But the widest rocket fairing available when Webb was designed was Europe's Ariane 5 rocket, and the telescope's mirror is more than 3 feet too wide to fit. So for Webb, getting to space requires folding and unfolding. The mirror and the sunshield, as well as the usual solar arrays and antennas, must all be neatly stowed for the telescope's launch. The mirror, made of 18 hexagonal segments, each 4.3 feet across, collapses like origami for the launch. Once in space, these elements unfold, locking together. The jigsaw puzzle is so finely tuned that once the mirror is fully aligned, the seams between the individual segments will be perfectly smooth. Aligning the mirror once in space will be an intricate endeavor for months, relying on one of the cameras aboard the spacecraft, the NIRCam instrument. At the backs of the 18 hexagonal mirror segments are small motors that delicately press onto the plates, shifting and bending them with extreme precision until they create one giant, perfectly smooth mirror. That means movement at the level of nanometers. There are 25.4 million nanometers in 1 inch. It's incredibly complicated, and that's why it takes so long to actually commission the telescope. Launched in late December, the first images won't come until the summer of 2022 because it takes that long to line everything up. The mirror also needed to be extremely lightweight. Had the engineers simply scaled up the 8-foot glass mirror of the Hubble Space Telescope to build the 21-foot mirror of Webb, the telescope would be too heavy for any existing rocket to lift. As it is, Webb's mirror is about an order of magnitude lighter per unit area compared to Hubble's mirror. Each of the 18 hexagonal segments, made of ultra-light metal beryllium, weighs only 46 pounds. The entire spacecraft, despite its enormous size, weighs only 6.5 metric tons, compared to the 11.1 metric tons of the smaller Hubble. The surface of the mirror is plated with gold, giving it this signature yellow tint. The golden color was chosen because it's the best for reflecting infrared radiation, much better than white or silver. The light reflected by the giant mirror is then concentrated onto the 30-inch secondary mirror that sits opposite the large mirror attached to the foldable tripod that must also deploy in space. From there, the light enters through an opening at the center of the large mirror into the telescope, where a Teteri mirror sends it to the detectors. One does not simply glance skyward to see back 13.5 billion years. No, the combination of technologies needed to make the James Webb Telescope possible is unique to this time period in human history. What we see through the telescope will no doubt change our ideas about humanity's place in the universe. So, are you excited to see the first images of a distant galaxy that the James Webb Telescope will send our way in just a few months? Let us know in the comments below. And if you want to watch more of our amazing videos, then stay tuned.